Okay, so we can jump right in and start talking about these conic section solutions to the two-body problem. Yeah, we derived them in the previous video in terms of math. Now we can talk a little bit more about the physics of what they actually mean as far as the trajectories of particles moving around in space. I showed this at the end. And on the right, I'm showing this, this effective potential function that I defined in the previous video. If you remember, when you take the conservation of energy and you solve it for the velocity, dr dt, the radial velocity, you basically get the square root of a difference between the energy, which is a constant, which we specify of the particle, minus this potential, this effective potential function of radius, which contains two different functions, right? Those two functions are plotted with the dashed lines up here. The positive one is the centrifugal potential, sort of a centrifugal barrier because it's positive, goes off, it drops off as 1 over r squared. The gravitational potential is negative. That's not shown in here, but it's, U is equal to minus G m over r, and that's negative. It drops off as 1 over r. So when you look at the sum of the two, at small values of r, the 1 over r squared centrifugal thing wins, so the total becomes positive. At large values of r, the gravitational part, the 1 over r part, wins, so it becomes negative. So it's always got to cross from positive to negative, and it always has the form where there's this global minimum in V of r called the minimum of the potential energy function, and you can write it out using the components of U and the centrifugal term as a specific constant that depends on the angular momentum and the masses, and all that, and the lambda, the scale size of the system. Right. So so we'd like to talk about these different solutions, and the best way, I think that the way that makes most sense of talking about the different shapes is to talk about the different values of the energy that those different orbits can have. Now, for the velocity not to be imaginary, E always has to be bigger than V. So I'm showing all these horizontal curves here of energy always sitting above the thick black line of V. E is always bigger than V. So we've got the different possibilities, and maybe we should start at the bottom of this list and work our way up, right? So when E is less than the minimum of the potential energy function, if E was down here somewhere, that's not possible because E would be less than V, velocity would be imaginary, and if you work out from the end of the previous video how to write the eccentricity of the orbit, that would correspond to a negative eccentricity, which is sort of a meaningless thing. So yes, that's not allowed. The minimum value of the total energy has to be equal to V min, and when the actual particle energy is equal to the value of V min, that corresponds to circular orbits. And you can actually see that by virtue of the fact that when you're sitting here at the minimum of V of r, and as you vary through your orbit at different positions in the orbit, there's really only one value of r that you could be sitting at. All the other values of energy have these horizontal lines where you can stay at the same energy at different values of r, but not true for the circular orbit. There's only one value of r, and get out a compass, and one value of r means circle. Yes. And of course, you can plug it into the solution to the differential equation, and that would show us that the r is equal to the lambda, the radius of curvature, is the actual radius for a circle. That's also 0 eccentricity. All right, increase the energy a little bit more, and you get these green lines here. These are the elliptical orbits, and if you look at the range of radii that you can be at different points in your orbit, it's a finite range. There's an r min and an r max that you have to remain between. And of course, you see for the ellipse, that's just as you go between the distance of closest approach, the periapsis, to the distance of furthest approach, the apsis, or perigee, apogee for if it's the Earth, perihelion, aphelion if it's the sun. You know these different terms. But it's a finite range. And the total energy is still negative because it's an orbit that's bound all the time. And it corresponds to an eccentricity between 0 and 1. Okay, if you keep increasing the total energy of the particle even more, now you come to these unbound orbits where there's a definite R min, but R max is infinity. Basically, the orbit can go all the way out to infinity, and these are the parabolic and hyperbolic orbits. You've seen these before. The main difference between the parabola and the hyperbola, other than their shape, is the fact that for the parabola, the energy is defined as being equal to 0 in the frame that we've defined here. And what that means, if I can go back, when you go to infinity, when R goes to infinity, the E essentially meets the V, right? If the effective potential goes to 0 as R goes to infinity and E is already 0, then that means that E equals V at infinity and the velocity is 0 at infinity. That's sort of the definition of the parabolic orbit. You can often talk about that in reverse, right? If you start off at an infinite distance with a 0 velocity and you let the two particles go, they'll eventually come in and swing past each other in a parabolic orbit. All right, and then of course, if you raise the energy at infinity even more, that gives you a non-zero velocity at infinity hyperbolic orbit. Again, we've talked a lot about the Coulomb collisions where two particles are coming in with finite relative speeds, and then they swing past each other and go off at finite relative speeds in straight line trajectories asymptotically. Okay, I think that's all the details. Yeah, and I've said a lot of this, right? For basically all the different types of orbits, you can often talk about an R min, but you can only talk about the R max for the circle and the ellipse, and they can be written in straightforward ways in terms of the properties. The V min we talked about. Oh, I guess I didn't mention that this solid black curve for V of R is actually only for a single choice of the angular momentum L. Different values of L will give you different shapes of that total curve. So there's really a whole family of curves that correspond to different L's, and then all the different orbits that can exist with respect to those are the different values of E that are possible also. All righty. So we can talk a lot more about elliptical orbits, right? Those are the orbits of the planets and the asteroids and comets and things in the solar system. Kepler's first law was just that the orbits are ellipses, and we've now proven that essentially. So there's all these geometric properties of ellipses that we could go through. I won't talk through them all, but we'll end up using a bunch of them as we go along. You know, you've seen the semi-major and semi-minor axes of the ellipses. Those are just sort of the radii in the two different directions as measured from the geometrical center of the ellipse. If you remember, of course, the orbit is centered on one of the foci of the ellipses, and thus the R goes from R min to an R max, which goes all the way over here. Oh yeah, the radius of curvature lambda that we defined geometrically is defined as this sort of half cross distance from the focus to the edge of the ellipse. Yeah, you can write the area of the ellipse. Of course, it's a generalized circle, right? It's not pi r squared anymore, but if there's an R in this direction and an R in this direction, A and B, it's just pi AB. All these things are sort of defined in terms of each other, and we'll come back to some of these and use them. Yeah, I think I've talked about just about all of these things already. Yeah, of course, we will also be going back to the inertial frame coordinates from our center of mass frame coordinates. And of course, the particles are moving, both particle 1 and particle 2 are moving with respect to the center of mass in the inertial frame. And I'm seeing that this animation is kind of not flowing well, but I've got the URL there, and I'll put the link in the description so you can see it better. But yeah, it's just interesting to sort of look at the behavior as a function of eccentricity and the relative mass ratio of the two objects, just to see what do these orbits actually look like in real space as you vary these parameters. I guess there's not too much to say here, but yeah, just take a take a look and see how various things are changing as the different parameters are changing. Yeah, also for elliptical orbits, we can now, we found Kepler's first law, we found Kepler's second law, we can now get the third law as well. And we can start with the second law. If you remember the second law, the equal areas being swept out in equal times, that was written as a dA over dt equals a constant. So we can rewrite that a little bit and put the differentials on both sides and integrate both sides as we sweep around this known elliptical trajectory with the focus, with the origin at one of the foci. So if we integrate, and if we actually integrate all the way around, start at some arbitrary point and then integrate all the way around the ellipse, well, the integral over time just goes from 0 to the period, the exact period of the orbit. The integral over area, if you start at some point and then you sweep out the entire thing, that entire thing is just the area of the ellipse, pi AB, as we said it. So, of course, the integral version of Kepler's second law is going to look like this, with the period being proportional to A times B. But now we can use some of the other properties of ellipses and write some of these things in. The A and the B can be written as A to the 3/2 times the square root of the radius of curvature by using the definition of the radius of curvature. And then the definition in terms of angular momentum and the masses can go in here. When Kepler wrote this, he squared both sides, and we see that a lot of things cancel out. Some of the masses, all of the angular momentum, L's cancel out, and what you get is that the square of the period is proportional to something that has to do with the masses times the cube of the semi-major axis of the ellipse. That seems to be Kepler's third law. Is it exactly Kepler's third law? Not quite, because remember what Kepler said was that all of the different planets of our solar system have this proportionality, and that the thing in parentheses, that proportionality constant, is just a single constant that you can use for all the planets. But if you look carefully, it's really not, right? The M is the reduced mass, and that contains an M1 and an M2, right? Mass of the sun, mass of the planet. The gamma also it's also G times M1 times M2. So this thing in parentheses depends on the mass of each different planet, but it turns out not by that much, right? If you write this in full, we can write the reduced mass as M1 times M2 divided by the total. And then the gamma is this other thing over here. The M1, M2s cancel out, and all that's left is the total mass. And of course, you know that the sun is much, much more massive by at least a factor of 10,000 or so than even the heaviest planet, Jupiter. So this is roughly equal to just the mass of the sun. So Kepler's third law is not an exact thing. It's only approximately true, but it's pretty close when the sun is much more massive than the planets. Yeah, there's other things. There's other ways we can write this, of course. I think in this course, you'll be seeing angular velocity a lot more often if we talk about things like accretion disks and shear flows of things in the plane of an orbit around a central source. So we can write the period as 2 pi over, we can write the angular velocity as 2 pi over the period, right? It's 2 pi radians per orbit. Period is seconds per orbit, so it's radians per second. And that actually simplifies things. The 4 pi squared gets canceled out by the 2 pi, and we just get a nice gm over r cubed under a square root. So this tells us that Keplerian orbits have angular velocities that drop off as r to the minus 1.5 power with radius, right? So if you have a lot of planets, they're not just orbiting all rigidly, they're orbiting much more slowly as you go out in r. What else? Yeah, we can go back and talk about the full Kepler problem, right? This was this idea of trying to figure out what are the exact trajectories of r and theta, both as functions of time. We haven't done that, and we can actually, there is a a path towards doing that a little bit more in terms of closed form analytic functions. So we can take this Kepler's second law to Kepler's third law thing, and we can actually integrate not all the way around the ellipse, but we can integrate part way, just from t equals 0 to some arbitrary time and over some arbitrary group of angles to get just a fraction of the area. Now, when we do that, the math gets a little nasty, but you can do it, right? This is just the same integral we did, but now instead of 0 to 2 pi, and over the entire period, it's just a fraction of it. You can work out, you can actually do these integrals analytically, but it's a kind of a complicated function of both theta and the eccentricity, but it is a function for t as a function of theta, and that's part of the whole problem of trying to get theta of t and then r of t. But yeah, doing the entire problem is not even as analytically possible as this. There have been many centuries of effort of pen and paper math trying to find these solutions. I think at some point they realized it's not possible, so people started to do series expansions. There's this thing called Kepler's equation that tells you about the difference between circular and equivalent circular and actual elliptical orbits. There are these angular quantities called anomalies. I'm not going to go into any of this stuff. Please take a celestial mechanics class if you really want to know more. I think what we have talked about in terms of the solutions are really all you sort of need to know as an astronomer, as an astrophysicist or a planetary scientist, about how the physics works of these types of orbits. These extra details are important for tracking orbits of objects in space, celestial mechanics. But yeah, it's a little bit beyond the scope of this class. All right, the other videos today are going to have to do with applications of two-body orbits, making changes from one elliptical orbit to another and other things like that. And there's one more sort of piece of mathematical apparatus that's good to have at our disposal, and that's going to be going back to energy conservation one more time. And this is now the simpler version of energy conservation. If you remember many videos ago, we separated out the kinetic energy into two terms, right? There was the r dot squared and then the r squared theta dot squared in these polar coordinates. But when you keep them together, it's just 1/2 mv squared. It's just a velocity squared. And you can solve the energy conservation for that velocity squared. I just did it sort of analytically on the right and wrote it in a slightly different way. And this is actually an interesting solution. It's the velocity squared in terms of constants that include, and the radius and the total energy. Now, it's normally not all that common to talk about the total energy of an orbit. So there is a replacement that we can do. For a circular or elliptical orbit, we can make use of this definition of the semi-major axis that we had a few slides ago. And actually, it turns out to simplify things quite nicely. The energy is negative for an elliptical orbit. So this plus 2e over gamma is actually a negative term, but all these other constants cancel out, and it's just 1 over the semi-major axis. So it's a really compact way of thinking about how does the velocity vary at different points r along an elliptical or a circular orbit. This is called the Vis-Viva equation. In Latin, that means the living force, and it's got a really strange history going back to the 1600s when people still didn't quite understand equations of motion. They had ideas of living force versus dead force, acceleration versus friction. They didn't quite have the terms for all this stuff yet. Yeah, so it's an interesting history to look at different debates between scientists back then. But really, it boils down to just sort of another way of thinking about Kepler's second law. The closer in you go, the faster it becomes, right? As r becomes smaller, the velocity becomes bigger because it's in the denominator. All right, okay, so yes, so we will move on and talk about these applications in the next one.